of BGA25, 24 even, getting ahead of myself. This session is on Bandage-NG with Anton Korobenikov. Please take it away, Anton.
Yeah, thank you, Damon. So let me share my screen. Hold on.
And I think we've frozen. Oh no, you're back. Hello.
Yeah, something strange. So the Zoom on my laptop kind of like locked the keyboard. So let me see if I can fix that. All right, so I think now we are ready, hopefully. So let's start. So we're going to talk about Bandage. So, and well, actually not the original Bandage, but the Bandage next generation. And but before we start, so let me just give a brief introduction. Who am I? And so I'm technically the Space genome assembler, but besides Space, I also contributed to some other genome assembly and analysis tools. Well, like as I said, so I'm is the technical leader, but probably the best uh, term would be used to be because, well, sadly, Spades is not going to be like developed and updated anymore much. I'm a big advocate for open source software, code sharing, and reuse. So, and I definitely support all the like joint development of the software, the use of open source software, the code integration, and so on. But my area of interest is not only bioinformatics. So I also contributed to other open source projects, so not even in bioinformatics. So and definitely feel free to contact me with questions via email or preferable via GitHub issues. So before we start about talking about the tool, let's briefly talk why we actually need to these like assembly graphs and so on. And that's quite interesting question because traditionally the whole bioinformatics and results of the genome assembly was, well, mostly centered about the like just contiguous sequences. And ideally, we wanted, well, in ideal world, we want to have the each species assembled separately into a set of contigs. So ideally, we would like to have just the one long contig per each chromosome, whatever it doesn't mean. And if we have multiple strains, then well, we definitely want all strain variations carefully phased out. However, in the reality, we cannot have the single contig per genome or per chromosome. So, and here is a little bit controversy, because if we consider the context as the result of genome assembly, then lots and lots of useful contiguity information, lots of information about the inter-contig dependencies and how they are go after each other in the genome is essentially lost. Well, and as for strains, we also have some controversy, because in many cases we are not able to shape the result. For example, different assemblers usually produce either strain contigs, so they shorten represent individual strains, or kind of try to collapse all the differences into the consensus contigs, so they're longer, they represent the backbone structure, but they might be not as accurate in the nucleotide space. So meaning that, well, the one size doesn't fit all, and we need to do something. We essentially need to go one step back and figure out what might be the proper result of the genome assembly, or what is the genome assembly result. I have one motivating example. So it's a little bit old, but still, I think, pretty useful. In the paper that was published almost 10 years ago, in all with co-authors, studied the hospital wastewater discharge method genome, I think in Singapore. And they were interested in the presence of certain antimicrobial resistance genes, like beta-lactamases and things like that. And their analysis was pretty straightforward. They used, so they did the assembly and then mapped the reads back to the context and do read-based estimation of abundances of antibiotic-resistant genes. So in that particular paper, 9 families of beta-lactamases were reported to be present in the sample with different variations. So, as I said, study used street mapping to assemble gene sequences to estimate the abundances and perform further typing, like what is the particular beta-lactamase and so on. So the trick here, or the problem here, is that typical beta-lactamase gene is around 200 amino acids, meaning that if your input is ordinary short reads, it's unlikely to reside on a single read. And then the reliance on the assembly is crucial here. Let's take a look into one of these beta-lactamase gene. So it's IMP4 beta-lactamase. It definitely is in the assembly graph, but spread over multiple nodes of the graph. Yeah, so it's there. So it's spread cross 1, 2, 3, 4, 5, 7, 8, 9, 10 nodes of the assembly graph. And the reason why it's spread, because, well, there are multiple families of beta-lactamases there, and certainly bunch of them, they just share the common elements. So everything is pretty much tangled here, and they form very complex repeat structures with all the considered things. But if we look into the scaffolds, we will see that the particular family, gene of beta-lactamase, it was not assembled into a single scaffold. So it was segmented into 2 different scaffolds here. One is blue and another was green. And as a result, the study simply missed that, because, well, it means that particular beta-lactamase gene, and for IMP4, it just reported 0 abundance. So meaning that, that is my take, is that the assembly graph, and it's the only thing that fully represents the outcome of the assembly process. Assembly graph include important information about the contiguity, what is following what in the genome or genomes in question. So it also includes the important coverage depth information and so on. And what we routinely use, like contigs and scaffolds, are essentially the annotations of certain assembly graph features. Like assembler inferred that, okay, these two nodes of the assembly graphs like likely would follow one after another in the final assembly. So, and my point is that the assembly graphs could and should be used for downstream analysis. Fortunately, recently, some decent amount of tools emerged for the analysis of assembly graphs, and I'm pretty happy to see the increased widespread of the graphs, especially for ungenomes. So that's great. So another thing is that with the assembly graphs, fortunately, we have more or less standard de facto that is used to represent them. So, so the format is called GFA, so it's graphical fragment assembly format. It's text format used to represent assembly graphs. And good thing is that as any other text formats here, like FASTA or FASTQ or whatever, could be optionally compressed. And many tools, Bandage included, support the zipped files. So you can just compress, drop in, and it will be supported. There are two versions here, like version 1 and version 2. They were designed with different aims in mind. So I would say version 1 is more assembly-centric, and V2 is more maybe like pangenome-centric, I would say. And our focus is V1 only. And currently, the latest version is version 1.2. I think it was released maybe a year ago, a couple of years ago, as far as I remember. Yeah, probably all the 2 years ago. There is a specification, so everything is more or less standardized. But still, for the sake of completeness, so let us follow briefly about what is actually inside. So it won't be any magic inside those guys. So overall, the format is pretty straightforward, I would say. So as I said, so it's text format, meaning that you can use your favorite text processing tools even to modify things like EWK and all the things. Everything is organized in so-called records, and records are lines. Like here, within the single line, we have tab-separated fields, like here. So essentially, these are like just tab-separated value format, but the length of each record or each line could be different in terms of number of records. The records are typed, so they have the type, and this is the first field. So first field is always record type, and it's always single uppercase character. Other fields, their meaning depends on the particular record type, and each record optionally might have the set of optional type tags, like here. So let's walk over the records. So the basic record, I would say, is segment. So it's represented as the S record type, and it represents a continuous sequence or subsequence. And we think that is something like the part of the genome or set of genomes in question. There are few required fields, and one of required fields is the name. Another one is the sequence itself. So sequence might be absent. So then you usually use the star character to represent this something that's absent, plus set of optional tags like here. If sequence is absent, we still need to know the length of the segment. And for this particular thing, the special tag must be present to indicate that length. So if you just drop this file for Bandage, so it will just show us this set of non-connected segments. Next important thing is the link. Link represented by L record type, and it represents the particular overlap between two segments. Links imply direct adjacency of segments in the genome. Like here, for example, V1 precedes V2. And this means that in the genome in question, so V1 should be immediately before V2. Link is from end of one segment to the beginning of another segment. So we implicitly think that everything is like bidirectional. So like genomes are bidirectional, right? So we have the like two strands, so we have the like forward and reverse strand. But but usually we don't need to store both strands. We only need to specify the orientation. So, and well, link is from the end of one segment to the beginning of another of another segment, plus the towards the orientation of each segment, and uh, optionally the segments might overlap. For example, in case of deep green graph assemblies or like overlap assemblies. So it also has the field for the figure of the overlap. So if they don't have any overlap, okay, we will have just 0M here as a thing. So if we add like to this set of segments from the previous slide, these two links. So well, we will connect V1 and V2 on the direct strand, and we connect from V1 forward strand to the V3, but on the reverse side. Another thing that well, similar to links, but this was added into a recent revision of GFA, is the jumps. So jumps again shows the connection between two segments. So they are in some sense similar to links, but they do not imply a direct genome adjacency. So think about scaffolds, for example. The genome assembler might indicate that, okay, so here are two segments, but I don't know what is the inside, right? Because there is like complex tandem repeat in the middle of some like tangled region that I cannot like untangle properly or reliably. But if assembler could like scaffold over, then in the assembly graph, this like connection between two different segments or like pieces of the genomes could be represented by a jump. So, so optionally, the jumps also may provide estimated distance on the genome between two different segments or represent a shortcut. Like, for example, if there is some particular variation, if there is, for example, the like insertion, and we want to keep that, let's say we have the like deployed assembly, and then we can have like two links, but we can like represent the jump to see that okay, so this is the insertion, and we might like jump over if necessary. So in all this said, so the jumps represent like segments relations across assembly gaps, like for whatever reason the assembler produced that. As far as I know, the latest version of assemblers already could produce the assembly graph with jumps. So this includes Spade's version 4, and I think Vercocop could also produce jumps in some cases. I might be mistaken, but yeah, probably. So and yeah, here is the example graph. So we have the just one link from 11 to like node like segment 11 to segment 13 plus two jumps like just connecting things. Again, this is just a bit for example, so not representing something real. Anyway, another useful thing, and this is kind of annotation, I would say, is the path through the assembly graph. So paths represent ordered list of oriented segments, and each consecutive pair of oriented segments is supported by a link or jump record. So they also may show the segment overlaps or estimated gap sizes. So again, name of the path is required, and the another field is the well, is essentially the list of oriented segments. If if there is the like comma separating the names of segments, that means that they might be supported by direct link, so directly genome adjacency, like in the case of first path, and for everything else, like semicolon represents that it's a jump. So we can optionally distinguish between, like if we have both link and jump between the two different nodes, then we can just represent two different paths, like unambiguously. So yeah, essentially it can represent scaffolds or like trace of some sequence across the graph. For example, many sequence to graph aligners, including graph align, SP aligner, or like HMM to graph aligners, including path tracer, produce the paths of like sequence or HMM on the assembly graph. Another feature is the walk. So it's again ordered list of oriented segments, but it was specifically designed for pan-genome use case. So it's only for graphs without segment overlaps, so like pan-genome graphs. And usually it represents the path of the particular sample across the pan-genome graph. And the fields are, well, as you can see, it's very centered towards the pangenomic application. So here is the sample identifier, the haplotype index, so we can like have multiple like haplotype paths. We have the sequence identifier in the sample, like chromosome 1, chromosome 2, chromosome X, whatever. We have like start and end position of the sequence of the path, so we can like, do not bother, for example, and just have some like not trace the whole path of the chromosome, but let's say one particular gene. And then is the like synthesis of just ordered walk of the segment, how the things traverse. So yeah, the format is pretty straightforward. So it can be even modified by hand, and you could use all that text processing utilities to even operate the assembly graph, like drop the paths or find the link or whatever, and even extract the subgraph if necessary. Important thing is, and I would say that is very, very brilliant thing that was added is the set of tags. So each record could have a arbitrary number of optional fields. And these fields are called tags, and they're always last after because these are optional, so they always after the fields that the required fields. Another interesting thing is that tags are typed. So each tag essentially has this like tab type value format, like separated by this like two dot symbol. The name is essentially it's two characters, normally uppercase. The spec reserves the uppercase for standard tags, and the lowercase names are reserved for end users. So essentially, if you want to like annotate your assembly graph with whatever you want, then you could just use the lowercase names for the tags, and the like consumers of the if they adhere to the specification, so they assume that they would produce like they would just ignore them. There are different types out here. So type it's single letter. So type A is the single printable character. I is just integer. F is floating point value. Z is like uppercase Z is printable string, possibly include space because things are type separated. J is JSON, H is byte array in hex format, or B is array in integers and floats. So you see on the slide here are like some examples of how the text might look like of different types. So yeah, this is pretty much the quick introduction to the GFA format. So it's not scary at all. All right, so let's proceed to the tool itself. So it's not something new, and Bandage is yet another bioinformatics abbreviation. Well, so it stands for the bioinformatic application for navigating de novo assembly graphs easily. The original Bandage was developed by Ryan Wick. I think it was his master thesis almost 10 years ago. I can remember that, like 10 years ago, we've been exchanging emails about, well, so he found a couple of issues in how we produce the assembly graphs in spades. So we also gave him a couple of ideas, things like that. So this is the like original Bandage. So, but well, as it happens, and it's pretty normal. So Ryan moved to something else. So and the development of Bandage effectively stopped several years ago, meaning that, well, there were no future updates. And because the Bandage itself used the Qt framework for the GUI and visualization, it definitely needs to be updated to the new version of the framework. And otherwise, we would be unable to run on the modern hardware, including, for example, Mac laptops or whatever. So also some things were a little bit slower if your graphs are larger. So certainly in the year like 10 years ago, we only bothered about small-ish graphs produced from just isolate assemblies. But, well, recently, well, we try to assemble large metagenomes. We have the like T2T consortium assemblies, well, like complete mammalian genomes and things like that. So for larger graphs, there was huge memory consumption, and there were workarounds for this, but requires like lots of hacks and pre-processing. So uh, I talked to T2T folks well, like a few years ago when they like used the original Bandage well, and they well said all that like hops and different hacks they tried to do when well they had to do in order to use the original Bandage with the like 2T size graphs. Also, original Bandage did not support any standard GFA features like paths or works or walks. Uh, there were no ways to save graph layout. So meaning that if you prepared some fancy figure for your publication, you have, well, like you have to ensure that your Bandage session won't crash, your computer won't reboot, and so on. And this even caused lots of problems in the controlled systems. Like, for example, like if there are like some automatic nightly updates for that, well, would just like reboot your laptop like automatically, especially when the it's the critical security update. So yeah, also there are like many things that I would wanted to add to that. For example, it supports on the blast for sequence to graph alignment, plus a bunch of things. So yeah, uh, and this is how Bandage-NG essentially appeared, because over the years I had some patches on top of Bandage that I maintained locally. I think that started from the path support plus some other things. So and eventually I decided, okay, so probably it's the time to well, just make the things public and do some other things, well, in my spare time that I had. Well, I not have, but yeah. So essentially, Bandage-NG is the fork of original Bandage. So it contains patches that I maintained locally, plus some new development and improvements that I contributed over the years, or a couple of times I had students or interns, so they also contributed a little bit. It's mostly around the new features and new speed up. So I really don't want to change the overall like workflow or how the things are working. So, well, because we have to build on legacy, and well, I think like user UI UX wise is Bandage is pretty solid. So well, don't break something that simply works. Plus, meaning that well, we are all mere mortals, and well, given that currently the buzz factor for this project is essentially one, because I'm mostly alone here, I wanted to also utilize better and latest approaches for certain things, including like release management, continuous integration, and things like that. For example, like these days, all the releases are just automatically built on the like on GitHub, so I don't even bother doing that. Uh, so yeah, and motivated by like all the metagenomes and all the like T2T consortium needs, I try to optimize as much as possible in terms of the memory consumption and time to load. Uh, Sorry, I was a little bit lazy to do the like up-to-date benchmarking, so I just pulled some old table. Uh, but still, so the comparison here is for original Bandage versus Bandage, well, old version, like I think 2 years old, but still, uh, depending on the graph, so we might see like 5x or even 10x improvements in terms of the graph load time and in terms of the like memory consumption. Plus, actually, there are much more developments since then. So yeah, the first and the I would say very important thing is that if you want to download the things, we well, I stopped to do the like the version releases. So Bandage in NG employs the continuous build. meaning that every tested feature that is in the development branch immediately triggers the snapshot build. So you don't have to wait for the bug fixes. You don't have to wait for the other things. So you could just download the latest snapshot, and well, you have all the features that were developed so far. This certainly complicates some things, including, well, if you want to hard code the particular version in your scripts, sorry for that, but well, I decided that it might be better because, well, release is something it's something that should be announced, etc., etc. But well, I just wanted to anyone to use whatever is available immediately, and because it's graphical application, there are some caveats of building them for yourself here and there. So meaning that there are snapshots and there are binaries for x86 Linux. We do have binaries for macOS, including both x86 and ARM binaries, so you could run on the modern laptops. Recently, well, I'm not Windows person anymore. I think last time I had the Windows on my machines 20 years ago, something like that. But yeah, I managed to have the Windows build of Bandage, and we have snapshots here as well. So they're a little bit experimental, but I think at least from what I can see into virtual machines that I was able to run, uh, it seems to be working. So yeah, so meaning that we covered all the major platforms. So, and if someone would want anything else, well, feel free to compile from sources and do whatever you want. So it's open source after all. But as I said, so I try to do my best to ensure that all these binaries will be available, and because they're built automatically. So you just go and download the things. Bandage itself has also command line interface. So some functionality is available here. Mostly it's the functionality that is possible to automate. So there are subcommands like load, image, info, struct subgraph, query paths, and layout graph and select layouts, plus a bunch of different options to customize the subcommand output. The command line interface is a little bit, so did not receive much attention recently. So there might be some missed things, etc., etc. As usual, patch is always welcome. But let's go through the basic functionality of Bandage. So later we will try to on the hands-on also to play with that and see how things go. So the very first thing is certainly you have to load the input graph. So you use either the command line load command, or you just go from the menu file load graph, and yeah. And after loading, you just have the blank screen. That's pretty normal because we try to not to do any heavy operations unless it's entirely required. And the very first thing is the graph information. So immediately after loading, you can see the basic information about the graph. So number of nodes, number of edges, link connecting the nodes, number of paths, number of blocks, and total length of the all the segments. So you can immediately know how large your graph is. And if you push that more info button, then you will have more detailed information, including the connectivity, including the coverage depth, some other information about node lengths, number of connected components, and so on. So I would say this is more or less required because the next step is the graph layout. So, and this is one, I would say, pretty tricky thing because graph layout is the visualization of graph on a plane. And the thing here is not all graphs could be drawn without self intersections. So that's just the first problem. Another thing, we want these visualizations to be, not only aesthetically pleasing, but also useful for the further analysis. There are lots and lots and lots of different graph layout algorithms out there, but not all of them are pretty useful for the kinds of graphs we are having. So plus, in addition, graphs are large. So You can see in the example, right? So we have, I think it's just the Zymer mock metagenome. So it's just 70 megabases like thing, but it's also pretty large. So like here we have like like 40K nodes and more than 50,000 edges. So and the many algorithms are pretty computational intensive. Bandage-NG uses state-of-the-art OGDF library for the graph layout. In particular, it used the so-called fast multi-level layout algorithm. And compared to the original Bandage, we also did a couple of improvements here. One thing is that we try to do the layout in parallel. So sadly, the OGDF does not support the parallel layout of the single graph component. But in any case, it does the layout of one connected component at a time. So we just split the graph into the pieces onto the connected components. We lay out them independently into separate threads. So meaning that in this particular case, we have two large components. In case of Zymer, I think the top one is the bacteria, all the bacteria, and the bottom one, I think there are two yeast we are having there. So and then reassemble them into the complete picture. Funny enough, even the like reassembling into the complete picture is also a little bit non-trivial like task as well. But anyway, so meaning that if you have multiple cores V and you know that it's not a single component, then yeah, some additional speed up might be possible. Here is link for the algorithm if you're interested. Another important thing is that oftentimes you don't want to like show the entire graph. You only want to like drill or deep dive into the particular subgraph. And there is the so-called scopes that could be specified here, which essentially extract the part of the assembly graph, and there are different scopes that you could utilize. Well, first scope is, and this is the default one, is that we just show the draw entire graph. We can limit the scope up to around nodes up to a certain distance. Like for example, if you are interested in one particular node in the graph, you just draw the neighborhood and do whatever you want with that. We can do the around similar things, but around paths or walks. So if you have a scaffold, for example, then you could just visualize the neighborhood of that particular scaffold, provided that you have the scaffold path. Also, and more on that later, so if you have some query and, well, there is the path of the query in the graph, you can also visualize its neighborhood. Plus, we can just filter using the depth range. And this is pretty useful thing for the metagenomes because, well, we could just, for example, throw the low covered of metagenome and focus on the high covered part or something like that. Here is an example of I just kept the part of the graph that is having the mean depth of 100 and max depth of 500. So we left only for, yeah. So you see the graph is much simpler here. Another thing it's important for the visualization is usually we want to analyze the graph and we want to reason about the graph, right? So there are different ways to color a single node. So this is how it could be specified. So the first thing is that, well, all the nodes are just gray colored. Another one is the default is everything just have the random colors, and we try to ensure that neighboring nodes have decent colors. One can also color by depth. So we have the independent scale and use different color maps. And here is an example. We color the nodes by depth. So you could readily see that, yeah, we definitely have different species with different abundances in the assembly graphs. We can also color by the contiguity. So starting from the node, we can just color differently immediate neighbors and far distance neighbors. We can color by GC content. We can use the GFA tag to infer the color, or we can just augment with the additional information and infer the color from some like external CSV columns, like CSV data, but more on this later. We have different color schemes that could be used. So they are used when nodes are colored by depth or GC content or the like some categorical value. I try to choose some of the like top quality color maps. So because recently there were lots of the development on the color perception, right? Plus some of these color maps are colorblind friendly ones. So meaning that if you publish in some journals or some books that have the requirements like to have all your figures colorblind friendly, then you can use this scheme. So I believe default Viridis and CVDs and maybe Parula are colorblind friendly, but well, so the names are pretty standard. So all these color maps, so they are like yeah, you could just select different color schemes and see how it will look like. Here is example, the same graph, but well, using the turbo scheme. There is so-called the reference GFA format, but it differs only that it prescribes the certain set of tags for the sequences. So in order to support that, we also show all the optional tags like on the segment. So if you select this segment, so it shows all the text here. And we also have the possibility to color by the value of GFA tag. Here, for example, we have like 4 different or 3 different references. So like red and well, other things are colored differently. So yeah, that is here. The coloring by GC content could be used to well quickly spot, for example, contamination in the assemblies. I think that particular graph is the cyanobacteria. So usually cyanobacteria have the like lots of symbionts, and oftentimes the symbionts are actinobacteria, meaning that the cyanobacteria itself have the GC contents around maybe 40, and actinobacteria are usually high GC, having the GC content around maybe like 75, even sometimes 80%. So, and this is what we are having directly here. So the greenish one is the cyanobacteria, and the orange one is the actinobacteria. So they have really different GC content. Plus, if you select the node, we also show the GC content of the node itself. So, yeah. Another thing is that we also can use the external CSV file to infer the colors. More detail on this later, but for example, if you have the binning of your assembly graph, then you could just, and you have the like set of bins for each of your node and paths, you can just, well, visualize your max easily because, well, we just like load your binning in the CSV, then choose the like bin color, and well, you can see all these like very nice looking figures to see like where all your bins are allocated, and then you can even like see the quality of your binning of your max. All right. Another thing is that by default nodes are labeled to show topology, or unlabeled to show the topology of the graph. So, but additionally, we can show the length or name or depth or whatever value is on the CSV column. So you could annotate your nodes and well, just show them. So I think Verco uses that pretty extensible. So by default, if you select the node, you can see the length, the coverage depth, the GC contents, tags, if any, on the node. And there are also buttons for some easy editing, so you can change the color or label. Also, you can select multiple nodes, but then we will show some common things. There is also the node lookup. So you could query the nodes by their segment names and orientation. So you could also rename the node, and well, by default, the node name is, as I said, so segment name and orientation you could rename. So there are 2 different ways how we can show the the graph. So this like single or double. Double means that we show both strands, but in many cases this is like not necessary. So in single mode, the orientation could be omitted. So we just try to infer whatever is drawn. In VLOOKUP, part here could select visible nodes by names, and it allows both full and partial name match. One of the important things of the assembly graph is the depth. So there are multiple ways to specify depth for the node by GFA text. So, Bandage tries to use all of them. So the first is, the most precise one is the DP, or like upper lowercase. So I think lowercase is for fly, and it's the average depth of the node. Other possible text that could be used for the coverage depth of the node is the camera count. Then we just, recalculate the node depth as, divide the number of chimeras on the length, but it's approximate because, we don't know the length of the chimera, sadly here. So it could be slightly off. Or like read count or fragment count, we just, again, normalize them. So if possible, ensure, and if you want to use the coverage depth, ensure that your assembly graphs have this DP tags, or, you have to do something to infer the coverage. So the edges, they connect different nodes, they connect different segments, and they correspond either to links or to the jumps. So if you click on the edge, so it shows the start node name, the end node name, length of the overlap, if any, type of the edge. So whether it's jump link or like ordinary link, and any tags attached to the edge. And again, you could select multiple edges. Bandage supports plenty of customization of the display of different nodes and edges. So, and there are multiple ways how you can do that. Well, first is pretty manual. You could just like point, click, change color, etc., etc. But much more customization is allowed by the GFA tags. So Bandage supports the set of GFA tags that could be attached both to nodes and edges. And one can specify custom label for the node, or it's reverse complementary. Same for the color, and for the color, one can use the standard like RGB notation, like similar to like HTML like things, or you could use any standard SVG color names, like so don't bother about the particular RGB values. For edges, one could specify the custom width of the edge, or could even change the way how the edge is being drawn, like pen style. Either it's the solid line, or dashed line, or dash dot, or like double dot, whatever. Plus, all these things could be added via CSV annotations, so not only for the text. So here is some like breakdown on the text in the Bandage-NG wiki as well. In addition to the node, we also have the path or walk lookup. So you can find all the paths by name. Paths are by default could be matched by unique prefix, so you don't have to, because usually the path is just that long scaffold name, like node one, length something, coverage, blah, blah, blah. So you don't have to like type all this long name, so you could have just node one and go in. When you look up the things, you could just zoom in to show the nodes of the path. And there are two possible actions you can even do. You could like select all the nodes, or like recolor all the nodes over the path, so you could like see that all like straight single color, like here, for example. So there's also a way to see the list of all paths in the graph. So if you just click on that, yeah. So if you could just click on that like path button, so it shows the list of all paths. So it shows the path length, it shows the nodes of the path, and it also allows refine by node. So if you enter the node name here, so it would show all the paths that contain that particular node. And if the node is just a single one, that it also shows the position of the node in the containing path. Like for example, here I selected the node that is in the scaffold twice, so it's part of the tandem repeat. So, and you can see that's in the position of 26K and 76K on the scaffold. As I already said, you can augment your nodes from the external CSV file. Currently, we only support colors and additional labels. So colors are loaded automatically if there is the column named color, like regardless how you spell it. So yeah, and sorry for any like spelling mismatches in the Bandage itself, because well, uh, like Ryan is from Australia, so it used the British variant, but sometimes well the US variants are also like also here, also there. So or one can choose column name for the colors instead. And one of the useful things is that instead of the individual nodes, you could also specify the path names, meaning that if you have the path, like scaffold paths in the assembly graph, and if you bind your scaffolds, so you can, well, like just load that CSV file and compare, for example, mag bins, and that provided by different binners. So this is pretty useful. Yeah, and this is just example for the Zyme actually of one of those binnings. Yeah, so just put it here, or you could also like click the and use the CSV data in the particular column for the node labels. I'm showing here like as example of mag, but for example for folks doing deployed assemblies have the CSV for like different haplomes, and well they just show all like if it's like the common haplome or well there is the like some ploidy differences, etc. Another useful thing is the graph search. So, well, and I think that was one of the things that was present in Bandage before even the tools that do those graph analysis emerged. So, graph search, yeah, it's allowed in the, like, if you push that button. Essentially, it treats the set of graph nodes as the database, and it sees the paths of queries on the assembly graph. It's not the proper like query to graph alignment in that sense. So it's more like Pullman approximation because it only performs the alignment to graph node sequences and then try to reconstruct paths from individual node alignments. So it might be not the best and not the ideal process, but well, it kind of works maybe in 80% cases. Certainly, if you have the possibilities that prefer proper tools for the sequence to graph alignment, including like graph aligner, SP aligner, path tracer, etc., etc. So, it also can use graph paths in addition to node sequences to increase specificity. So essentially, you could like align to the scaffold sequences and not to individual node sequences. So if you push that button, then you will see that graph search dialog shown. We do support different aligners. So the blast mode that's the default and it's from the straight Bandage, it supports both nucleotide and amino acid queries. So it could do both like nucleotide and translated search. Hammer mode it allows alignment of hidden Markov models, both like nucleotide using an hammer and amino acid HMM using like a straight hammer. And for these particular things, Bandage does necessarily like 6-frame translation and coordinate conversion for you on fly. And there is also a minimap, so you can, let's say, align the long grids and see their paths through the assembly graph. The typical workflow is essentially like 3 steps. So you start from building the database, then you load the queries, and again, your queries might be just in FASTA format, or your queries might be HMMs. So then you probably set up the health filters or add command line parameters, like number of threads to use. Then you run the search and check the hits and the resulting paths. So after the graph search finished, we can then search the annotation on the assembly graph. Yeah, my example is that I loaded the 16S, 23S, and 5S like ribosomal RNA models from Barnard project. So and well, perform the search into this nice E. coli assembly graph. So all the features on are summarized in the form of annotations. So we might at the same time have multiple pattern annotations like hammer hits, like blast hits, bad features, all these kind of things. Usually you start by switching to gray colors, so then you could see the things, and there are different color schemes for the hits. So solid, they're colored by query, and here's an example of solid. So I think the green is 23S, blue is 16S, and red is 5S. Yeah, right. So, or there is the rainbow when the hit is just colored by the query coordinate. So if you could just open the annotations, you double click here, then, well, you could just choose what is there, like either solid or rainbow. So so you could see like if I'm switched from solid to rainbow, so then the things would be like recolored according to the coordinates. So it's quite useful to trace the path and see where we're at. Also, we kind of support the bed annotations. So if you have the bed file for your nodes, then you could just load, and we support all the standard bed things like blocks, thick parts, etc. And show them on the assembly graph. So certainly you could use the existing converters for the other formats. One particular thing is that I know that some of these formats have, like, produce non-standard bed files, so you might sometimes need to filter the results, like just dropping the like some non-standard columns. But yeah, we do support all of them. Uh, as I said, one of the important thing is the layout. So when you perform the automatic layout, then you even move your nodes and edges, so you could see the results. And if you want to save that particular layout, so you could just like save it or reload it for the further work. So you don't need to bother that like something's crashed or your laptop rebooted and you lost all your fancy picture and you cannot reproduce it anyway. So no. And actually, we do support two different formats. One is like fine-grained bandage format with like different like part of like node segments and bands, or the common format that could be used for like other downstream tools that just coordinates like of the like not like median coordinates of the node segments. There are different ways how the graph could be output. So you could copy and save selected node sequences or path sequences. You could save the subgraph both to a GFA or FASTA itself, or you could even like throw the like your web browser and do the blast search of the sequences of your nodes on the NCBR server. So that might be also useful to see like, oh, what is this strange like node shared by multiple species, right? So throw it in search, see, okay, yeah, that's the ribosomal gene. Okay, so that's kind of expected. There are also different settings. So, but the few of the important things that you probably might want to tweak often is the first is the so-called node length per megabase. The problem with the visualization of the assembly graphs is that, we normally could have very long segments, let's say the like entire like megabase. And at the same time, in the like technical regions, we can also have the very short ones, right? And therefore, we need to have kind of like scale that shows both long and short, like short nodes at the same time. So, and Bandage employs pretty, I would say, simple strategy. So first of all, there is the minimum node length. So the node length can be like less than minimum. And for everything else, we just specify the node length per megabase. So meaning that it's here. So meaning that the larger the value, the longer the nodes would be. There is also some auto detection that tries to do some things depending on the N50 and depending on the larger nodes, but depending on your graph, so it might be off. Sometimes it might be like even if even like by multiple like orders of magnitude, but still. So again, you can just choose the node length per megabase and redraw your graph to see like the impact of that. So yeah, that is the one of the example. So so this is from the like large, and that is from the small. So you could see we're seeing the different node lengths, right? So here we have like longer, like long nodes, and here we like shrink them and see the like more that variation structure of the graph. Another feature is the graph layout settings. So for the purpose of like aesthetically placed layout, we actually represent nodes as multiple segments. So to allow possible bands of the nodes. So and like smaller segments and means that we have like smoother nodes and like possibly like more bands. But that means that for the underlying layout have to deal with much more complex graph, so that complicates the layout. That is one thing. So so you want to decrease the node segment length if you want like more smoother nodes, or you want to increase if you want to shorten your layout time. The graph layout, it blocks into the like multiple iterations. So the more iterations we do, the better layout is in terms of like node separation, segment separation, and like self overlaps and stuff. But certainly it requires more time. There are also two different ways how the graph could be laid out. There is like the default one is no constraints. The linear graph layout tries to lay out graph into the single line. So this is more appropriate choose for the pangenomes, because then you have just multiple chromosomes like with difference and so on, and you really want that like straight line with like bubbles of differences. And another setting is the component separation, so it's just space between multiple connected components. There are a few things that are currently, I would say, work in progress. So yeah, here's spoiler. Well, or teaser, like first of all, there are some ideas how we can support additional node links. So think about Hi-C or TELSEC connections. So the basic support is out there, but definitely more ideas are needed to make this useful feature, because for Hi-C links, usually we have like connection of like almost every segment or every node with any other node. So we need to have some kind of like filtering and all like to make this actually useful for the like curation applications or like other visualizations. There are some ideas for some UI and UX improvements, some better error reporting. There are some ideas how we can probably even improve the graph layout. While I think the RGDF as a library is pretty solid and the default mode is pretty great, but it's not the best solution for the pangenomes. So meaning that probably we need to have some special pangenome mode, but I'm not a pangenome person at all. So meaning that someone should come with like more ideas and even maybe contribute. So, but in any case, so any ideas are always welcome, because I really want to to have the useful tool. So it's not that, because it's more like the pet project. So I'm not like interested in like publications and graphs or whatever. So therefore like my only aim is to have the tool that might be useful for the community and for other researchers. Meaning that so yeah, more ideas the better. So we can try to work together to see if something that you want to add, and we can see if it could be made generally useful. So meaning that we're not going to add like whatever crazy idea you might have. So no, we are not going to integrate genome like mag binning or whatever thing inside. So it's better to do it by separate tools. But yeah, whatever could be improve the analysis. So ideas are welcome. Oh, as I said, better yet. So if you can even contribute your patches, so you're always welcome. It's open source after all. And I think that's all for the overview part. So we can have a few questions, or if not, we can just move to some hand-ons.
I think you kind of covered absolutely everything in that presentation, to be honest.
Uh, well, I have not touched more about the editing because it's a little bit
Mm.
advanced things for first of all, and I don't want to touch editing because, well, uh, if you try to edit things, well, it's most either suitable to curation or, well, you kind of change the underlying structure, meaning that, well, you need to be pretty cautious, so it's not just like point and click. Okay,
I
then
think
let's,
Sergey
yeah,
covered it. Sergey covered it a little
yeah,
bit in the Verco talk the other day.
yeah, yeah,
Um, so yeah,
right.
we kind of got everything.
Right. So well, let's just see how the things are go. And let me switch to another window. All right. So right. So Gitbot is uh, done in the way that automatically fires the Bandage-NG. So yeah. So but for this, you need to ensure that you enable the all of the like pop-up windows. All right, so here we are. Okay, so let's actually work from pretty much the same things. So in the assets, I collected a couple of the assembly graphs. So let's start from the like that just equally assembly graph. So we load that. So we can see the graph information here. You can see the total length is, yeah, it's pretty okay. So it's like from the basis, just pretty straightforward. Uh, so we have the like okay, so we have like 70 or so 600 nodes. We have three connected components on this later. So well, median depth is 200x. So I think we're pretty good. The N50 is on the graph, so it's 60K. Well, it's fine as well because I think for the short read assembler, you cannot go with 450 beyond that 110K due to the particular repeat content and repeat structure of E. coli genome. Uh, so here we can also start by drawing the entire graph, but we already could see what's on the paths as well. So yeah, there are like multiple like scaffold paths, so we could see directly here what's going on. Okay, let's just draw the graph and see what is there. So yeah, you could see, well, this is the graph obtained from the latest space. So there are also some jumps, and you could see essentially the jumps connects the dead end parts of the graph. So let me see if I can, oh, it kind of zooms the browser, but not the picture itself. That's weird. Uh, all right, that's probably the outcome of the BNC session. Sorry. Uh, yeah. But anyway, so you can see that we have a couple of dead ends here, but we have the scaffolds that connected these dead ends with the like probably scaffold parts. We could click on the nodes, yeah, see what's going on. You can click on the edges and paths, so you can see that it's indeed the jump link. So yeah, we can also limit our scope, for example, around the, let's say, around the very first scaffold. Yeah. So the first scaffold itself is pretty fine. So we can see that it contains multiple nodes, right? And we can see it has even some like complex repeat structures that probably were resolved by the assembler here. It's fine. So we can even see if, yeah, so there are like something in the neighborhood. So yeah, that's usually the first thing that you could do with the assembly graph, just see around what's going on. Okay, let's again draw the entire graph. We can see how the different colors occur here. So yeah, we can color by the depth. So and by default, because it's the color by the depth, you could immediately see the like some of the repetitive structure because, well, they have different things. They are like yellowish colored. We can also go to the settings and change the well, the scheme, so to see its impact on the result. So it's not immediately applied though, so you have to click OK. But yeah, that's kind of like this. Or we can even try some other scheme. So not the turbo, but yeah, let's try this just in case. Yeah, we can try to do multiple things on this graph, but let's, yeah, so you could like throw the names, unfortunately, because we cannot easily zoom in, well, we don't see the well, the things here reliably. Sorry for that. I think we can find some node, or we can even like, draw the graph itself, and now still too small. Yeah, sadly, but okay, let's select just one node. So here it is, and then interesting. Oh yeah. I guess it's something with the BNC section, so it kind of does not show the fonts properly. I know. Oh, the size was wrong. Okay. Yeah, now it's better. So probably due to VNC section, it was unable to infer the size for the font properly. Frankly speaking, I saw this for the first time. Yeah. Anyway, yeah. Now this year, I think that's great. Yeah. So certainly things could be pretty messy if we like enable all the labels. So yeah. Let's try to do the graph search. So and switch to gray colors. And let's just replicate that hammer search of the 16F sequences. So I switch to hammer here. Then I click on the build hammer database. I collected, so in the assets, so you have like two HMMs, one for like it's for bacterial ribosomal genes and HUC for eukaryotic, just in case. So we load there. So let's run hammer, and I think we're having like 4 nodes here. So for hammer, I need to use like to put the like CPU here, and let me also have the p-value threshold as well by default. So we can just enable it here, and now we can run the hammer search. So below is the set of all hits, like with node names. Well, we don't have the percent identity here because we're aligning HMMs. For the blast, we definitely have the percent identity here. We have the alignment length, we have the query coverage. Again, in the blast case, we will also have the number of mismatches and gaps. Well, and here are the coordinates, or the query of the node plus some like e-value and bit scores. Here also we having the reconstructed path for the particular queries. So overall, we can see that there are like total number of hits, the overall query cover by the paths, and if you click here, you can see 2 different reconstructed paths. So, well, this one I just on the like entire node, for 23s, yeah, and here contains like multiple nodes as well. Now we can close the thing, and we can like find the annotation subpage, double click here, choose solid, and now we can see where all these things reside. So we can even try to like, no, sorry, draw around the curry heads. So let's do probably something like this. So yeah, maybe even more. I just wanted to have some connected thing. Yeah. All right. So you can see that indeed this looks like the like ribosomal operon. Definitely the topology of the graph suggests, right? So there are like multiple copies, right? All these like unresolved bubbles, etc., etc. Well, we know that for E. coli there are, at least for the 16S. Yeah, and that's like the typical repetitive structure here. So you see there is that repetitive edge and like two inputs and two outputs, and well, we don't know if the assembler was able to connect inputs to outputs here, but plus definitely because we know how many copies are there in the coli, if it's 6 or 7, I don't recall. Well, definitely assembler collapsed a couple of them, but well, that's fine. All right, you can switch to rainbow to see even the coordinates. So like red means the beginning of the query, and well, as usual, the violet means the end of the query. So I would probably say that this thing might be either misassembled or something strange happened. But anyway, yeah. Plus, if you click text, you have the annotation. All right, let's try to do something else. So as I said, so we can load also the like the arbiter annotation for the nodes. So let me switch to the entire graph, and I have also what I did. So I took all the node sequences and I run the gene predictor here, and here is the bed for all the predicted genes. Now you can see in the annotation there is also the bed, and we can there are plenty. But if you get solid, you can see that these are all essentially the gene predictions on the assembly graphs. So in this particular case, it might be not entirely useful, but in many other cases, well, so you could certainly have your own features and you want to see where they are in the assembly graph and do something else. All right, let's try to do something larger. So here is the Zyma metagenome. So I think it's mock metagenome, I don't recall, like 11 or 12 species here. And I think we having two yeast species there. So one being the like normal, like as like normal typical yeast, and another one is some cryptococcus, plus some other bacteria species. So yeah, again, we can see the overall statistics, like what we have here. So then, all right, so let's see what we have on the path. So we have much more scaffold paths, but you see we have much more like longer scaffolds here, like one of the scaffold being like almost like 100 and oh, sorry, not 100, but 1.5 megabases. So don't default that the like length here and the length here does not agree. This is the graph from the older version of Spades. So that emitted the assembly graph in the like pre-GFA 1.2 format. And then we did not have the way to represent the scaffold paths. So actually one of the motivation for the jump links added to the GFA 1.2 format was to represent the jump links. So we can represent the scaffold paths properly. Now here we just essentially, well, have to split like in this split into like one scaffold into like multiple segments. So here's the first segment. like with the like suffix 1. Here is the second segment with the suffix 3, and they should be somewhere like another piece. So yeah. I did not rerun the assembly here because, well, I did not want to like rerun the binning on top of that. Anyway, so let's try to run the graph layout here. It would take a while because it's much larger graph, and well, it's only like 4-core system, and after all, we're running in the cloud. But I think it would take not that long, maybe a minute or two, something like that. At least it used to be yesterday when I tried everything.
So have you experimented at all with 3D graphs, like displaying
Uh,
these in a 3D space?
uh,
Because
well,
it probably
that's
wouldn't be particularly useful, but it would be cool.
right. So, well, like, it's it's very interesting thing actually, and it's all about our like human perception of things. We, despite living in the three-dimensional space or like four-dimensional, if you take the time, we comprehend the information much easier, like in 2 dimensions. Maybe because we like just like learn to like read the books or like write on the like into the like two-dimensional spaces on the planes, but something like that. So maybe it's just because we've been taught that from our childhood, and if we like just start teaching like our kids like to think and reason in the 3D, they will have much better sense of that. But yeah, I think that while it might open much of the possibilities, definitely for the like graph layout in the three-dimensional space, but well, I'm not sure how it could be useful from the user. Yeah. All right. So we finished the layout. Still, multiple cores helped because, well, definitely we had this layout for this company separately. Uh, I already told you that the upper one is probably bacterial and the lower one is the yeast one, so they don't connect to each other. Fortunately, we can double check this using, well, so here are the GC content. So yeah, you can see that they even have, let me switch the color scheme. Uh, yeah, well, usually Jet or Turbo, pretty high contrast ones. So, well, certainly if you have some perception difficulties, they might be not pretty great, but let's try Turbo. So yeah. So yeah, this is so currently we are colored by the GC content, right? So and we can see the different parts of these mag have really different GC contents. Like this part definitely, oh, I cannot easily say that plenty of notes, but anyway, you could see that I can select a bunch of things. So it's like I selected almost like so meaning that the probably 2 genomes here because the total length is like seven megabases. So that's twice the typical bacterial length. So yeah. But anyway, uh, that's like that. So we can also see how the thing goes by the depth. Yeah. So and here in the bacterial part, pretty much everything could be similar depth, but in this part, we definitely see two different pieces, right? Having, well, pretty different depths, like maybe even like 3 different pieces, something like that. Let me let me load the CSV data. And in our case, it's just the metagenomic binning of this graph. So important thing is that you really like in Spade's case, we emit the scaffold path in the assembly graph. So meaning that in order to visualize everything, you really need to bin your scaffolds, not context, scaffolds. We don't have the context paths. Sorry. So names won't match. So you simply won't have anything. So Yeah, so you could see that there are like multiple bins, and some of those bins are even more or less look like similar to the. Let me just reduce some clutter. Like they are like look similar to the uh, well to the difference in the GC content, meaning that well we're pretty good, but at least in the genome part we definitely see some mixed things. Sadly, I cannot zoom in easily in the VNC section, but I have one note uh, that I found yesterday. So yeah, so here it is. So this is the particular part. Let me probably just throw the things around this node. So it's 296099. So and yeah, so we are actually here. Okay, let me redraw, and then we can zoom in. Apparently, would work better here. So this is the node that is common multiple species. So and often if you analyze the max, I mean, it's good thing to see like, and to find out what are those like common nodes. So yeah, let's and then well figure out if we're expecting. Yeah, so this is the node, but it connects to the other nodes out here. You can see, right? So there are even like multiple bins, so it's definitely the place there, like multiple bins collide, right? So we can even check what's going on. Uh, so one so one easy thing is even to try to do some kind of blast, right? So we can even do the web blast selected nodes. So let me start that and see where we are. So yeah, we have quite nice hit to the Salmonella enterica, and let us see where we are. So do we have any annotation here? Well, probably not. Not. Okay, well, it's been. Yeah, looks like the annotation for that particular region is well. We probably need to select some other string, something that is annotated properly. Yeah, maybe this one would be better. Oh. Anyway, while we're here, let me redo the search. And again, doing that, like loading both like bacteria. So that would be the chaotic. right? So we already have our thing here. So just let's run the search. So it would take some time because things are much larger here. No, we don't have the proper track here, sadly, for these hits, but it just happens. Yeah, we're still waiting, but that's just because we are like matching 70 megabases towards this like six different, not six, 7 different models. Right. Another thing, if you're doing, if you try to, like for that web blast search, there is a limit, so we cannot. Oh, so we finished. All right, so I think we have pretty decent results here. So we have like multiple, like 16 SPARs, multiple 23 SPARs. So, and then let me do this particular thing, then let me. Interesting. So why don't we see anything here? Okay, let me. Yeah, but yeah, sadly we don't have the easy thing to zoom out here. Yeah. Anyway, so here you can see. Yeah. So and you can see that's exactly one of the tangled place where like uh like multiple mags connect to each other, right? So that's exactly the point. So usually, well, when you deal with the mags, so they are connected via, well, very conservative regions, and usually it's the ribosomal genes that are very, very conservative and that, well, connect your mags together. Uh, Sadly, we don't have the good solution to that. But besides that, you can see that everything is pretty well separated. With well, certainly we do have some unbinned pieces here, and if you want, we can even like manually enrich our mags, right? So this probably just was too short, but we can just double check what's going on and see who is this guy. Yeah, so it's some bacillus. So I think it should be Bacillus subtilis or maybe even B series. But yeah, it looks like it's yeah, pretty conservative region for the Bacillus genome itself. So, but one thing that I wanted to show you as the last, as here, you see, uh, like we have two different bins, like very, very like into this test, right? So And usually in this particular case, it would be great to see what are those guys. So certainly it looks like they have plenty of things in common. And well, Bina seems to do quite decent job like separating them out, right? But still, it would be useful to think like or to reason who they are. So again, let's try to do some easy things like do some blast search. So this is quite long node, so it's 22 kilobases. So if we try to do that, so it will just fire the browser, but well, won't copy here because of I think 10K or 50K limit. But the particular sequence was put into the clipboard. In my VNC case, the clipboard is here. So I need to copy manually and paste it here. So that would be our first search. And let's see what would be the next guide here. All right, so the first guy is definitely Salmonella enterica. So could you guess what might be the second species here that is pretty close to the Salmonella in terms of the genome organization? It shares a lot. Oh yeah, we've been timed out. That's sad because I forgot that we have like the time limit, and I didn't not do anything in the console. But funny enough, that was the last thing that I wanted you to show. So we have not lose much, but anyway. So the second species is certainly E. coli. Well, yeah, that's pretty standard problem that in the in the MAX when you have the both Salmonella and E. coli, well, they're usually very, very interspersed. Oh, something seems to be not working properly. It's fun. Anyway, I think that was the last thing that I wanted to show you here. So we can probably conclude on that particular note. So all the data is in the Git pod. So feel free to take use of that. So these are all public data sets. So yeah, you can play with the data and see what's going on. Well, I think that's it for the Bandage. So again, if you have any ideas, suggestions, problems, feel free to like open the issue on GitHub or catch me. So yeah, that's probably all for now. And I think we're even more or less in time.
Yeah, thank you very much. It's made me realize quite how old a version of Bandage we must be using at Sanger. So gonna have to get on that.
Yeah, just like open the about page and see
Yeah.
what's there.
Yeah. Yeah, does anyone have any questions? Or should we let Anton get on with his day? No, it doesn't seem like anything. Well, not the GitHub, the
Oh,
Discord will
so
be there. So if anyone does
there
have
is a
any questions.
question. There is a question.
Oh yeah.
So yeah, sadly the documentation is not pretty in the good shape as of now because I did not have much time to work on that. So one particular area when everyone could contribute is definitely the documentation. So some of the documentation for the like legacy vanilla Bandage still applies, but not that much. So let's consider these slides and this talk is kind of like substitute for documentation for now. So yeah. Sorry,
It's fine.
not the best answer, but well, patch always welcome. As I said, so I'm not quite a pangenome person, so I don't have much experience with working with pangenomes. Well, so yeah, maybe we need to have someone else to show some state-of-the-art examples how the pangenomes could be analyzed. But well, my understanding is, well, again, it depends on what you are having in the beginning. So if you have the pangenome graph with walks and so on, and or you have the annotation of like different so you can color the things. So yeah, you can just use it straight away. But again, there might be some tags that I'm not aware of or not thought of. So yeah, I just simply did not do much analysis for pangenomes.
There is, just to tack onto that, Sergey Koren is
Yeah.
doing a second session on T2T assemblies with Verco, where he does use Bandage to show off some of the graphs that they've generated.
Yeah, but in case of Verco, it's usually you only like visualize two different paths for the for the deployed assemblies, so you know where the different hasloms are, and well, you could even see if they like match another. Well, like so far the usual limit is the amount of resources you are having. Like T2T folks are pretty happy with using Bandage, with the mammalian graphs with the gigabases. One particular trick is if it might reduce the memory consumption is to put the sequences on the side if you don't want to use the things like search or whatever. So, but we do have some limits on the segment size, but it's in I think it's around maybe 2 gigabases per segment, like per node, something like that. So you should be fine with almost any project I can imagine. So
Cool. All right. Anything else, guys? No?
yeah. And
well,
speaking of the old version using Samger, so depending on what is the version used, so probably if you upgrade, then you will have the quite nice speed up, especially if you're
yes.
using the early versions. So
yeah, because some of the sizes of some of the genomes that the assembler guys are generating definitely tax it. But then again, they are
but
on the very large size of genomes that they're playing with. We'll definitely get something to upgrade, because I like the only thing that irked me about Bandage was on the edge of the plots where you would get the scaffolds that would curve away from everything. Obviously, using your newer version, that doesn't happen anymore, and they all curve when you move them, which is very nice, just from a UX point of view.
Another thing, so as you saw, so we kind of open 100 megabases metagenome in the cloud instance, and it kind of works. So it could be even improved even more, but for now I think it's very okay. So plus also some other features that I know that one particular limitation was that vanilla Bandage had the Windows build, and we only were able to get that Windows build only this summer. So this thing might prevent the use for in some cases. So, but I think Windows kind of works, at least for my very limited testing. Well, and I kind of expect that it should work. So yeah.
Yeah.
So yeah, at least I don't see any more things that would prevent this from the platform perspective.
Cool. Right. Should we call it there then?
Yeah, probably. If there are
Yeah.
no further questions.
Well, I don't think so. Right. Well, thank you everyone for turning up. Thank you, Anton, for giving up your time to run the session. It's been fantastic. And I hope to see you all in the next one.
Yeah. Thank you. Take care.
Right.